Welcome everyone to this session on reinforcement learning, and today we're gonna learn about the environment. More precisely, how to predict transitions from one state to another. And we will see how to use Markov chains for doing these kind of predictions. Let's take a look at the reinforcement learning feedback loop, where we have an agent that takes actions and interacts with an environment. But if the agent takes actions, it's not certain that it will end up in a certain state as that it wants to end up in. And also it's not clear what the reward will be. So these are uncertain stochastic variables. And if we unroll the problem, we can see that each step has states, actions, and rewards. And the states and the rewards actually are stochastic. So we can use this sequence of state and action and rewards actually to look only at the state and the rewards and look at how to model the sequence as a stochastic process. So there are many ways to model these kind of processes, but if we take a look at the real world data, we see that there are usually some patterns that are recurring. So the laws of the process, they do not change over time. And also what we can see in observations is that it's a short history that is already sufficient to predict future states. Now, one example is weather predictions. If we want to predict the weather of tomorrow, well, we can use the same model that we have used to predict the weather of last week. And the patterns of the weather changes will always be the same. The weather itself changes, but the laws of motion might be described by the same model. Also, we don't need to go back 3 months and look up what the weather was back then to predict tomorrow's weather. It's sufficient to look at the past few days to predict tomorrow's weather. Also, for text prediction, if we have a sentence, then, well, if there is a verb missing, then we might use the grammatical rules to use the prediction of the next utterance. And so the grammatical rules might stay constant, and the way the text is composed, the patterns might stay constant. However, well, the sentences, of course, have different words. So, but to predict these words, it might be sufficient to look at the past few sequences of the text to predict the next sentences. Now, let's look at how to model these kind of transition dynamics by using Markov processes, and let's look at what actually are the Markovian and the stationarity properties in these processes. Now, to zoom in a little bit, let's just focus on the states S and the stochastic dynamics that are described by a probability distribution that is conditional on the past history. So if we start in state 0 and end up in state st-1, then given that, what is the probability to go to state st? And here is a graphical description of this, where we have random variables in circles, and we see here state 4 actually depends on the entire history, so we have 4 arrows pointing to this state. Now you might ask yourself, how can we model this? This is going to be an infinitively large conditional distribution. And you're right, that's a problem. So there is an easy solution that makes some assumptions that try to actually make this work in practice. And the first part of this assumptions is a stationarity assumption. So the idea is that the dynamics do not change over time. And the second property of these processes would be described by a Markovian assumption, so that only a finite history of past states is sufficient to predict the future states. Now, with this information, we can actually model a first-order Markov process that describes the probability of ending up in state ST given the whole history by just taking a look at the last state ST minus 1. So then the problem simplifies a lot. Well, someone might argue, well, this is not a good model, so what about the other states in the past? Then we can say, well, let's take a second order Markov process and include also the state ST minus 2 to model the probability to get up to end up in the state ST. Now, when people talk about Markov processes, however, they usually think about the first order stochastic process, where we have only the last state that is relevant, and also that this conditional distribution is the same for in each time step. The advantage is that we can specify an entire process with just a single conditional distribution, the probability of ending up in state S prime, given that we have been in state S. Now let's take a look at some examples. Marrying is one example, and I have some real-world data where we can take a look at this. So here the states could be the relationship history, and the dynamics could be the age. Another example would be robotic control, where we have positional variables x, y, z, the coordinates that describe where the arm is currently, and theta that says something about the angle of the arm. And then the dynamics are a constant motion. And you might also criticize this constant motion. It's not constant. The velocity changes, so you have acceleration. And then you could in principle, also include acceleration as another set of state variables here. Inventory management is another example. Here the states would be, well, the inventory level. And the dynamics are the demand. And demand changes from each day to the other. However, the way it changes could be assumed constant. Of course, this is not always the case, but it might be a good approximation to that process. Now, once we have this process at hand, we can actually do predictions k periods ahead. So we predict what is the probability to end up in state ST plus k, given that we are in state ST. And using the chain rule of probability, we can write this up as the probability of each individual transition, which is here then multiplied up k times. And then we sum that up over the intermediate states. Now, if we have discrete states, we can write this as a matrix, transition matrix, capital T, that has dimension S times S, and that represents then this k ahead probability. Now, because we have the stationarity assumption, each transition probability between two time steps will be the same, so we can actually multiply this transition matrix by itself k times to get a prediction. And the complexity of this is k times the cubic number of states. So the more states we add, the more complex this calculation will be. Now let's take a look at a simple example to get some understanding of how this could work. Now here we have an initial distribution of the probability of being never married or being married, which is 50-50. And we can write up a transition matrix as follows. So if we are in the current state never married, the probability of staying never married is 1/2. However, the probability of getting married, if we have been never married, is also 1/2 in this example. And if we have already been married, then going back to being never married is 0%. And if we are already married, well, we stay married with 100% in this example. Now, it's easy to take the square of this matrix and also the other powers. So we can do some k-ahead predictions with this. So we just multiply this probability distribution vector with the transition matrix that we raise to the power of k for all the k years. So it's easy to verify that if we multiply this vector with the transition matrix, we come to the probability of being never married after 1 year is 25% and being married is 75%. After 2 years, it's 12.5% and 87.5%. And then, it moves on like this. So almost everyone is married after 5 years. And in the long run, eventually everyone is married. Now, if we use real-world data on young women born in the 1950s, we can do the same exercise, and we see here in green the initial probabilities around 50-50, and then after 5 years, almost all the women are already married, and in the long run, everyone gets married. Now you might say, well, this process is not Markovian, or it might be not stationary. The solution is to add new state components until the dynamics are then Markovian and stationary. Now, marrying, here the probability might depend on how long a woman has been single, her past relationship history, the norms in 1970s versus 1980s, and so we can add variables on this. But the question is where to stop, because we have here a trade-off. If we include more state variables, then the computational complexity will increase significantly. On the other hand, if we do not do that, we might end up in a process that is not Markovian and not stationary, which would not satisfy our assumptions. Now, predictions themselves are not really useful in reinforcement learning. We want to take actions. We actually want to predict and take actions based on those predictions. And that's the topic of the Markov decision processes that we will take a look at next. Here's one reference on reading up for Markov processes. Just to summarize, the Markov processes are useful to model stochastic processes with probabilistic transitions. And the first order Markov process that is also stationary, that simplifies the prediction a lot. Adding more state variables can restore the Markovian and stationary properties, but that comes at a computational cost. So we will use those predictions of the Markov processes for Markov decision processes. So thanks for watching and see you in the next video.